Welcome to this lecture. The topic of today's lecture is the law of rotation of our galaxy. I would like to tell you how astronomers have determined this rotation curve of our galaxy. In 1914, an astronomer by the name Vesto Slipher discovered the rotation of this galaxy, whose catalog name is NGC 4594. NGC stands for New General Catalog. He discovered that this galaxy is rotating with a rotational velocity of 200 kilometers per second. Within 3 years, by 1917, he had measured the rotation of 6 spiral nebulae. Now, I'm not going to tell you how he measured the rotation of these galaxies. I would like you to think about it and figure it out yourself. If you can't figure it out, then read about it. Soon after that, a Swedish astronomer by name Bertil Lindblad made the following extraordinary discovery. He noticed that there are a few stars in the solar neighborhood which have a large velocity relative to the local standard of rest. And I've tried to sketch these stars with large velocities with respect to the local standard of rest. What is this local standard of rest? It is true that the sun and all the stars in its vicinity are going around the center of the galaxy. But there are also random motions due to gravitational encounters with other rotating bodies. Therefore, the motion of stars is not a perfectly circular motion. It's a slightly jittery motion, and the random motion could be in any direction that you like. So astronomers define a local standard of rest in which, by and large, the sun and the stars in a small volume can be considered to be stationary with respect to one another, and then this whole local standard of rest is going around the center of the galaxy. Now, what Lindblad discovered that there are some stars in the solar neighborhood which have a large velocity with respect to the local standard of rest. That is fine. But what was important is that such high velocity stars exhibit a curious asymmetry. There are far fewer high velocity stars in one particular direction than in the opposite direction. From this observation, Lindblad deduced the sun and the other disk stars in the local standard of rest rotate rapidly past the other population. So the high velocity stars seems to be streaming past us in the opposite direction. So if you're going in a river in a fast speedboat, it'll appear to you that the coast, everything on the shore of the banks of the river are going in the opposite direction. So Lindblad deduced that the reason for these high velocity motions is that the sun and the other stars in the local standard of rest are streaming past these stars so that the high velocity stars appear to be streaming past us in the opposite direction. Now from the fact that there is a curious asymmetry, namely if I look in the opposite direction, then I don't find this phenomena, he made a very important discovery. He deduced, that is Lindblad deduced, that our galaxy is in fact rotating differentially, just like the planets in the solar system are rotating differentially. In other words, planets at different distances from the sun rotate with different angular velocities. And that's what is indicated in this picture there. Therefore, the extraordinary conclusion by Bertil Lindblad is that our galaxy is not rotating like a rigid body, but it is rotating differentially. Jan Oort, a Dutch astronomer who lived till a ripe age of 92 and made monumental contribution to astronomy, wrote a classic paper in 1927. And in this paper, he quantified the differential rotation discovered by Bertil Lindblad by introducing two constants A and B. What does differential rotation mean? The sun is rotating around the center of galaxy with a certain angular velocity omega. That omega is not constant as a function of the radial distance from the center of the galaxy. And the question is, how does this omega vary with the galactocentric distance? What is d omega by dr, where r is the distance from the center of the galaxy? So he introduced two constants, A and B. So let us first get the geometry right. Here is the sun. It is going around the center of the galaxy with a certain angular velocity omega sun. It has a circular velocity which is tangential to this circle, that is denoted by theta, theta subscript sun for the sun. The relationship, of course, is that the circular velocity of the tangential velocity theta of r is equal to r omega. So both theta and omega are functions of r, where r is the distance from the center of the galaxy. Now we are looking in a particular direction whose longitude is L. This is L equal to 0, L equal to 90 degrees, 180 degrees, 270 degrees, 360 degrees, and so on. So here I have for you, for the sake of convenience, I have written for you, theta is r omega. Therefore, the variation of the circular velocity with respect to the galactocentric radius d theta dr is equal to omega plus r d omega dr, which is a straightforward first derivative of this equation over there. So let's keep that in mind. Now, what Oort said was that as long as we are considering stars in the vicinity of the solar neighborhood, not stars very far away but quite close by, then the radial velocity of the star with respect to us in the sun is given by d sine 2l multiplied by a constant which is known as Oort's constant A, where L is the longitude. As I've defined the longitude in the picture I showed you before. Similarly, the transverse velocity or the proper motion mu, which is the transverse velocity divided by the distance to the star, is given by A cos 2L plus a second constant B. So A and B are Oort's constants. So if we know the constants A and B, then we can derive the radial velocity of nearby stars as well as the transverse velocity. What are these constants A and B? A is defined as 1/2 of theta over r minus d theta by dr evaluated at the solar neighborhood minus 1/2 of r d omega dr evaluated at the solar neighborhood. This relation in terms of theta I have written in terms of omega by using this relation over there. Please verify this very simple expression over there. Quite clearly, this represents a shear, d omega dr, the rate at which the angular velocity is changing with respect to the distance from the center of the galaxy. So it's a shear. To remind you once again, theta in these expressions is the circular velocity or the tangential velocity, and omega is the angular velocity. Now let us write the expression for the Oort's constant B. Oort's constant B, which is needed to define the transverse velocity. Remember, the velocity vector of a star can be decomposed into a component which is along our line of sight, which is the radial velocity, and a component which is perpendicular to the line of sight, which is the transverse velocity. So this is vorticity. So in order to derive the radial velocity and the transverse velocity, we need to describe two things about galactic rotation. One is the vorticity, the curl or the rotation part of it, and the other is the shear, which is the rate at which it is changing with respect to galactocentric radius. Where did these two relations come from? Well, it is a matter of very simple trigonometry that I don't want to waste time doing here, but if you're interested, you can do that, and I shall show you a figure to enable you to set up this problem, and it's a matter of 2 or 3 minutes. You can derive these two expressions. So there is a summary, namely, the radial velocity of nearby stars and the transverse velocities can be defined in terms of two constants A and B, known as Oort's constants, which are given by this formula over there. Now, if you are interested in deriving that expression, then do the following. Here is the sun, here is the center of the galaxy. The sun is at a certain distance, r naught or r sun if you like. We are looking in some longitude L. This is the longitude L, and there is a star. The star will have a velocity. It's going around the center of the galaxy. Therefore, that velocity, which is the green vector, will be tangent to this dashed circle. Remember, the velocity is always tangent to the circle on which the star is located. So, all you have to do is to derive the radial velocity. You have to decompose this velocity into a radial component and a transverse component. Radial component will be obviously v cos alpha, and then the transverse velocity will be v sine alpha. Now, you do a simple trigonometry and convince yourselves that this will give you the expression that I had given before. And the most important thing to notice about that expression that I gave is both the radial velocity and the transverse velocity are proportional to sine 2L and cos 2L, where L is the longitude. Therefore, it is not sine L or cosine L, it is sine 2L, and that comes from very simple trigonometric identities, and you can convince yourself that these expressions come from a simple Taylor series expansion of the value of the angular velocity of the sun about, and the gradient of it about the value at the solar circle. So you do a Taylor series expansion of omega of r and theta of r about their respective values in the solar neighborhood, and you will get that expression that is given over there. Now notice that if I subtract b from a minus b, the second term in this bracket cancels out, and therefore what we will have is simply half of 2 omega with a plus sign, which is omega evaluated. Remember, these brackets are evaluated at the solar circle. Therefore, A minus B will give you omega at the solar circle. So if you could determine A and B by observing nearby stars, then A minus B will tell you the angular velocity with which the sun is going around the center of the galaxy. Now in 1927, Oort estimated the value of A was 30 and the value of B was minus 10. Well, this doesn't tally with modern values. According to the modern values, A is 14.8 kilometers per second per kiloparsec. B is minus 12.4 kilometers per second per kiloparsec. All right? So these are the modern values. So from this, A minus B, I can derive the angular velocity of the sun. And since the circular velocity theta is equal to r times omega, I can derive the circular velocity of the sun and the stars and the local standard of rest, and that comes to 220 kilometers per second. Therefore, to summarize, one can deduce from observing the nearby stars and resolving their velocities in terms of radial velocities and transverse velocity, one can deduce the circular velocity of the solar neighborhood, and that is 220 kilometers per second. Just for your reference, the Earth is going around the sun with a velocity of 30 kilometers per second. The sun is going around the center of the galaxy at a rate of 220 kilometers per second. So how long will it take for the sun to go once around the center of the galaxy? It will take about 230 million years to go around the galaxy. How long will it take if you use present-day rockets? It will take about 10 billion years. So that's all one can deduce from observing stars in the solar neighborhood. Now we want to determine the large-scale differential rotation of the galaxy. What we really would like is the law that relates the angular velocity or the circular velocity theta of r as a function of the distance from the center of the galaxy. That will give us the law of rotation of the galaxy. How do we determine this? Clearly, we cannot do this by observing stars because we can only see the stars in the local neighborhood because of severe extinction due to dust in the galaxy. So you need a probe to look towards the very end of the galaxy in order to have even a chance of determining the circular velocity and its dependence on the galactocentric radius. So Oort had an idea. So since Oort relied on the motion of stars, his analysis was restricted to the solar neighborhood. He sought for a method which will enable him to find the radial and transverse velocities throughout the galaxy. Now remember, to measure velocity, you are going to use Doppler shift. To use Doppler shift, you must have a precise frequency, and you must know what is the value of the frequency in the laboratory. Therefore, from the observed frequency, you can tell whether the source is moving towards you or away from you. So what you need is some sort of a signal at a precise frequency, at a wavelength which does not suffer any extinction due to dust in the galaxy. So Oort asked his student, Henk van die Hulst, to think about the feasibility of detecting the 21 centimeter radiation from the hyperfine transition of the ground state of neutral hydrogen atoms. You remember we discussed this when we discussed the interstellar medium. So let us quickly review what we discussed. We started out by discussing Zeeman effect, which is the splitting of the energy levels of an electron in an external magnetic field H. We said that a particular energy level of an electron in a magnetic field will be split into two levels. One, which is the upper level, in which the spin angular momentum of the electron, the intrinsic angular momentum of the electron, is parallel to the magnetic field, and the lower level is one where the spin of the electron, or the spin angular momentum of the electron, is anti-parallel to the magnetic field. And this difference in energy, delta E, which is h nu, is given by 2 mu b times h, where mu b is the Bohr magneton. It is made up of fundamental constants. So this is the magnitude of splitting of an energy level of an electron in an external magnetic field. But we are not talking about an external magnetic field. We are considering the ground state of a hydrogen atom. The electron is in n equal to 1 level of the hydrogen atom. It has a ground state energy of minus 13.6 electron volt. Now here is the problem. Both the electron and proton have spin angular momentum equal to 1/2 h bar, where h bar is h divided by 2 pi and h is Planck's constant. In Bohr's theory of the atom, there is no spin. But the moment you introduce the spin of the electron and the spin of the proton, you have to allow for the possibility that the spin of the electron and the spin of the proton may be parallel, and the spin of the electron and the spin of the proton may be anti-parallel. And those two will have different energies, exactly like in our Zeeman effect problem, and there will be a splitting. And that splitting has an energy level difference of 6 micro electron volt, extremely small splitting. And the frequency of radiation that is emitted when a hydrogen atom jumps from this upper level to the lower level is 1420 megahertz to some 10 decimal places. It has been measured. Or the wavelength is 21 centimeter. Again, the wavelength has been measured to any number of decimal places. So we will, for shorthand notation, call it 21 centimeter wavelength, although the wavelength is known incredibly precisely. So this is the 21 centimeter radiation of the hydrogen atom. And Oort knew that there must be a lot of hydrogen atoms in the interstellar space. So if you could detect the 21 centimeter radiation from hydrogen atom, then using Doppler shift, we could determine the motion of the hydrogen atoms and decompose that motion into a component which is along the line of sight, which is the radial component of their velocity. So that was the idea. Now, there is a problem. Why was this radiation not detected on Earth? I explained this before. Let me state it once again. So the radiation that we are talking about is spontaneous emission of radiation, namely a hydrogen atom in the upper hyperfine level in which the spin of the proton and electrons are parallel jumps to the lower level where the spin of the electron and proton are anti-parallel and emits a photon whose wavelength is 21 centimeter. Now we can ask, what is the spontaneous transition probability that a hydrogen atom will jump from this upper level to the lower level? Now, quantum mechanics enables you to calculate this transition probability. If you consider the Bohr's theory of hydrogen atom, for example, I can use quantum mechanics and calculate what is the probability that an electron in the n equal to 2 level will spontaneously jump to n equal to 1 level, or get absorbed from n equal to 1 level to n equal to 2 level. And that's what quantum mechanics enables you to do. If you now do a quantum mechanical calculation, you get this extraordinary result that the transition probability from the upper to the lower level is an incredibly small number, which is 3 times 10 to the power minus 15 inverse second. Therefore, the reciprocal of this, which is roughly how long the hydrogen atom will stay in this level before spontaneously jumping to this lower level, is the reciprocal of that, which is roughly 10 to the power 7 years. So if I have hydrogen atoms in the electronic ground state, they will mostly be in the upper hyperfine level, which is this one where the spin of the electron and proton are anti-parallel. And if you leave it there undisturbed, then once in 10 to the 7 years or so, it will jump down, bingo, emit a photon of 21 centimeter wavelength. Now therein lies the difficulty of observing this radiation in the terrestrial conditions, because The reason is that since the lifetime of the upper level is very long, 10 to the 7 years or thereabouts, long before the atom jumps spontaneously from upper to a lower level emitting a photon, various perturbations, various collisions will cause a radiationless transition, namely the atom in the upper level will inelastically come down to the lower level by giving away some energy to a passing by atom which collided with it. So that goes away with a little extra kinetic energy. The point is, although the hydrogen atom has jumped from the upper level to the lower level of the hyperfine levels, it has not emitted the 21 centimeter photon. The energy has gone in some other mode. That's why it's difficult to observe this under terrestrial conditions. Now, Van der Hulst was one of the students working with Jan Oort in Leiden, in the Netherlands, in Holland. At Oort's suggestion, Van der Hulst investigated whether the 21 centimeter radiation could be detected from the hydrogen atoms in interstellar space. In 1945, Van der Hulst wrote a very famous paper in which he concluded and argued that this radiation at 21 centimeter could easily be detected from interstellar hydrogen atoms. And the reason why it could easily be detected is because the number density of hydrogen atom is very small. Remember our discussion of the interstellar medium? The number density is only of the order of 1 atom per cubic centimeter as opposed to 10 to the power 20 or 21 atoms or molecules per cubic centimeter in the room in which you are watching this video. Therefore, there is a finite chance that the atom in the upper hyperfine level will spontaneously jump to the lower level emitting this photon. So, two gentlemen, Edward Purcell in Harvard University and Jan Oort in Leiden in Holland, decided to build equipment to discover this radiation from interstellar space. Now, whenever your professor wants to make a major discovery, first thing he does is to get hold of a good student who will then do all the hard work. So there were two students, two groups, one led by Oort in Leiden and the other by Purcell in Harvard. And the two students were, Edward Purcell's student was Ewan and Jan Oort's student was Müller. Now, and they both discovered this 21 centimeter radiation from the interstellar hydrogen atoms in 1951. But there's an interesting story which I promised to tell you when we discuss the interstellar medium. Now, what happened was that just as both the teams were very close to constructing the necessary horn, the antenna, if you like, to detect 21 centimeter electromagnetic waves and the necessary amplifiers and so on, Müller's laboratory in Leiden caught fire. And so all the equipment that he had built was burned. Now, this is something that will never happen today in this cutthroat day of doing science. Edward Purcell knew that had it not been for the fire, that Müller would also be able to detect this radiation. What happened was that Ewan and Purcell detected this radiation, and instead of within a millisecond announcing it to the press and going to television and newspapers, what he did was send a telegram to Jan Oort in Leiden, in Holland, in the Netherlands, saying that, look, ask your student to rebuild his electronics. He will detect this radiation without any difficulty. I will wait till then to publish this paper. And so it had transpired that the papers by Ewan and Purcell and Müller and Oort were published together in 1951. This is something that will not happen today, but thank God such days did exist in the past. Undoubtedly, this was one of the most important discoveries in the entire history of astronomy because of its impact, as I already explained when we discussed the interstellar medium. So, If you now have a radio telescope operating at a frequency around 21 centimeter, remember these hydrogen clouds are moving and therefore the frequency at which they will emit or absorb will not be the rest frequency of 1420 megahertz, but it will be either blue shifted or red shifted, so your electronics must have some sufficient bandwidth to detect this Doppler motion. So if you point the radio telescope in some galactic longitude, this is what you discover. These are the red dots is the data. Now what a radio astronomer does is to decompose this data using a computer, in the old days calculator, and fit it to a set of Gaussians that are shown here. 1, 2, 3, 4, 5, 6, 7, 8, 9 Gaussians. Therefore this observed emission profile has been fit to 9 Gaussians. That means there are 9 discrete hydrogen clouds which are responsible for this emission. And these hydrogen clouds are moving at different velocities, and therefore the emission comes at different frequencies. Now notice that these velocities are negative as well as positive. In other words, some clouds are moving away from us, some clouds are moving towards us. And you notice that there is a maximum positive velocity beyond which the emission cuts off, which is roughly around 8 or 9 kilometers per second. Good. Now, what do we do with such an observation? That I shall try to explain through a series of very simple diagrams, but you have to listen very carefully. Let us now, this is our galaxy. The dashed circle is the solar circle. In other words, the sun goes around the center of the galaxy on that circle with a certain angular velocity. Let us say that there is a hydrogen cloud on the blue circle. Let us say there are 2 hydrogen clouds, one over there and one over there. They may be in other directions also, but we are looking at a particular galactic longitude L. This is longitude L equal to 0. This is longitude L equal to 90 degrees. This is longitude L. So what do you expect? First thing you expect is the following. Both these clouds will have the same radial velocity. What is radial velocity? Both these clouds will have a velocity vector which is tangent to the circle at that point, which is tangent to the circle at this point. So to get the radial velocity, I have to decompose it in that direction, decompose it in that direction. And if that angle is theta, then it is v cos theta, it will be the same. In other words, the radial velocity of both these clouds will be the same. Therefore, you will not be able to tell whether the cloud is here or there. You will only be able to tell it they are on the same circle. Now, what will be the sign of the radial velocity? Remember, the galaxy is rotating differentially. Therefore, clouds or stars in the inner galaxy will be rotating faster than stars in the outer galaxy. Therefore, the angular velocity of these clouds will be larger than the angular velocity of the sun in this circle because of differential rotation. Therefore, the radial velocity will be positive. In other words, it will appear to us that these clouds are actually receding from us, which is positive velocity. So I hope you have understood what I have said. So you look in point your radio telescope in a particular galactic longitude, you are going to see clouds at all sorts of distances from the galactic center. We have first used a filter to discuss only clouds on this blue circle. But what about other circles? Let's consider that now. So let us consider a cloud on a circle which is of a larger radius than the radius of the solar circle. Now, we know because of differential rotation, the angular velocity of this cloud will be less than the angular velocity of the sun because the sun is interior to it. Therefore, since the cloud here is outside the solar circle, its circular velocity will be less than that of the sun. and therefore it will have a negative velocity. Therefore, if I look, I'm still looking in the same longitude L, but I'm now looking at a cloud which is at a larger distance from the center of the galaxy than the sun. It will have a negative radial velocity with respect to us. Now let us consider a cloud which is on the solar circle, this red dot over there. So please remember that everything on the solar circle is going around with the same angular velocity around the center of the galaxy. Therefore, the velocity of this cloud is tangential 90 degrees. Therefore, there will be no radial component of this velocity. Therefore, the radial velocity of a cloud, all clouds on the solar circle, will have zero radial velocity with respect to us. Now let us look at a very special distance, the green circle. Let's imagine that there is a cloud over there. Its circular velocity will be tangent to it, which is the green arrow. Green arrow is tangent to the green circle. But please notice that that tangent is also coincident with our direction of the line of sight at this particular longitude. In other words, the black line, which is the line of sight, is also a tangent to this green circle. Therefore, the radial component of this cloud, this green cloud, there is no need to decompose it. The radial velocity of that curve will be precisely equal to its tangential velocity, because cos 0 is 1. Therefore, and of course, since this cloud is interior to the solar circle, it will have a positive radial velocity. The point I want to emphasize here is that this radial velocity in this particular longitude will be the maximum of all values. Why is it a maximum of all values? Because at this particular location, the velocity of the cloud is tangent to the circle, which is also along the line of sight. Therefore, the cos theta is 0, and therefore it will appear with the maximum radial velocity. Now let's put all the clouds together. Please notice that there is no tangent point in the outer galaxy. If I were to look in that longitude of say 135 degrees, there is no tangent point. Those circles are larger than the solar circle, therefore it will cut the circles. It can never be tangential. So tangential direction can only be interior to the solar circle. Okay? So how to deal with the galaxy exterior to the solar circle? We'll come to that presently. So now let's put back all the clouds in our sample along this longitude. But before that, please notice that I know exactly the distance at which that cloud is from the center of the galaxy, because this angle is 90 degrees. Therefore, this distance r of this green cloud from the center of the galaxy is r sun sine theta L, where r sun is the distance of the sun from the center of the galaxy. So now let's put back all the clouds. But before that, let us appreciate the following. So the reason for stressing on this tangent point is the following. Because we have now identified this feature at the maximum positive radial velocity as coming from this green cloud on the tangent point, whose distance from the center of the galaxy is now uniquely determined by this relation r is equal to r sun sine L, we have determined the circular velocity of this green cloud, whose distance from the center of the galaxy we know. Therefore, theta r has thus been determined. Wonderful. So we have now determined, by looking in this longitude L, determine the circular velocity at a particular special distance from the center of the galaxy. Now let's go and look at all the clouds that we saw in this longitude L. So there were the two blue clouds on the blue circle. They will have, first of all, the red cloud on the solar circle will have zero velocity. Then the magenta cloud on the circle outside the solar circle will have negative radial velocity. The cloud on the blue circle will have positive radial velocity. There will be a distance ambiguity because both these will have the same velocity. And then this green cloud along this longitude will have the maximum radial velocity and it's positive. And we have now identified that velocity as the circular velocity of that cloud around the center of the galaxy. Now all we have to do is to repeat this procedure at all longitudes interior to the solar circle. How does it work? Let's now consider looking along that longitude. So that is the longitude. So once again, there will be clouds. Let's say there is a cloud on this circle, it will have negative velocity. That cloud will have zero velocity. And that cloud, blue cloud, will now have the maximum radial velocity. There will not be any green there because that is interior. There will be blue feature here is the maximum positive radial velocity that comes from this tangent point. And I know the distance of the tangent point from the center of the galaxy, which is given by r sun sin L. Now let's look in some other longitude. Then the line of sight is tangent to some other circle. Therefore, the maximum positive radial velocity will come from this cloud. Therefore, by doing these observations at all longitude interior to the solar circle, we can determine the circular velocity of the clouds at all values of r interior to the solar circle. In other words, we have determined theta of r as a function of r, which is what we set out to do. But this is not the entire galaxy. There's also a galaxy beyond the solar circle, but we cannot use this technique of tangent point because, as I said before, if you look away from the galactic, if you look towards the galactic anticenter, there are no tangent points. You will intersect all the circles. So before going that, by doing such observations at all longitudes, astronomers have been able to reconstruct the distribution of neutral hydrogen in the galaxy. This method also provides us with the rotation curve or the law of rotation of the galaxy. Now, this method can be used only inside the solar circle because there are no tangent points outside the solar circle. That should be clear from this diagram over there. So that is the red cloud, that is the magenta cloud, that is the blue cloud, and there is no green cloud. That is from the previous slide, pardon me. So now we have repeated it, and then we have determined the circular velocity at all r up to the solar circle radius. What about beyond that? So what astronomers do is the following. You look away from the center of the galaxy and look for a molecular cloud. There are plenty of them. And you detect the molecular cloud through the carbon monoxide emission from J equal to 1 rotational level to J equal to 0 rotational level of the carbon monoxide molecule. And since there is a precise frequency of 115 gigahertz, using Doppler shift, you can determine the radial velocity of this molecular cloud, just as we determine the radial velocity of the hydrogen cloud using the 21 centimeter radiation. Similarly, you can determine the radial velocity of the molecular cloud using the carbon monoxide emission line. But how do you determine the distance from the sun and therefore distance from the center of the galaxy? So there, astronomers rely on the following feature. If you remember our discussion of molecular cloud, I said that at the very outer edge of the molecular cloud, the cloud collapses and forms a cluster of stars. Because of ionization fronts and supernova shockwave compresses the molecular cloud, and like a blister, you have star formation at the edge of the molecular cloud. Now, these are very bright stars, newly found massive blue stars. And astronomers have other ways of determining the distances to these blue stars. So you can determine the distance to the blister. So you do this in a two-step process. To determine the distance to the molecular cloud, you use the blister on the molecular cloud and determine the distance. To determine the motion of the molecular cloud, you use carbon monoxide molecule to determine the motion, and through the Doppler shift, you determine the radial velocity. So the rotation curve has been extended well beyond the solar circle by measuring the velocity of carbon monoxide molecules in the molecular clouds. The distances to the molecular clouds is inferred by measuring the distance to the ionized hydrogen clouds lit up by the newly formed stars near the surface of the molecular clouds, namely the blisters. So using these two techniques, astronomers have been able to determine the law of rotation of our galaxy. Before I tell you what they found, let us anticipate what we expect. So let us say that this shaded region is our galaxy, a sphere of uniform density for simplicity. And the galaxy ends here, and this is all outside the galaxy. The blank region is outside the galaxy. So what do we expect the law of rotation of a hydrogen atom to be, which is going around the center of the galaxy? Now let us look at the inset here. Let us consider one of these three black dots interior to the mass. So the gravitational force acting on the black dot is G, mass enclosed within it, multiplied by the mass of the body divided by r squared, where m enclosed, if you're considering this, is mass interior to that radius. If you're considering this, it's the mass interior to that radius. If you're considering this, it's the mass interior to that radius. So gmm by r squared is equal to the centrifugal force mv squared over r. Therefore, the orbital velocity v, or theta according to our previous notation, is square root of gm capital M divided by r. What is the mass enclosed within? That is the volume 4 by 3 pi r cubed multiplied by the density. And there is an r in the denominator, so it will become 4 by 3 pi r squared multiplied by rho multiplied by g is the orbital velocity. You remember this is Kepler's laws. So the orbital velocity will be equal to this thing in the square root multiplied by small r divided by capital R, where capital R is the radius of the mass distribution and small r is the distance at which you are from the center of the mass distribution. Therefore, inside the galaxy, considered here to be of uniform density for simplicity, you expect the circular velocity to be proportional to r. In other words, as you go from the center of the galaxy outwards, the circular velocity will increase linearly. I hope that is clear. Work through this algebra yourself. Now let us look outside the mass distribution, these 2 points. So you have left the galaxy behind, you are outside. So it's like the planets in the solar system. You are no longer inside the sun, you are outside the sun. So it's the same thing. The orbital velocity is this is now Kepler's laws. G rho 4 pi by 3 r cubed divided by r. So, that's of course the mass. If you're considering the sun, that will be the mass of the sun. 4 by 3 pi r cubed times rho will be the mass of the sun, and that is Kepler's law. So Kepler's law tells you that if you are outside the mass distribution, the circular velocity or the tangential velocity or the orbital velocity will decrease as 1 over square root of r. That is Kepler's law, right? Fine. So now, if you put the two things together, what you expect plotted on the y-axis is the circular velocity or the tangential velocity or the orbital velocity as a function from the center of the galaxy. So, as long as you are interior to the distribution of mass in the galaxy, the circular velocity will increase linearly with r, and afterwards it will decrease as 1 over square root of r. So that is what you expect from Newton's laws or Kepler's laws. What do you find? This is what you find. So what is plotted on the y-axis is the circular velocity or the orbital velocity or the tangential velocity as a function of distance from the center of the galaxy. After the initial rise, it is absolutely dead flat. And there is the sun's location, about 8 kiloparsec from the center of the galaxy. And you notice that this circular velocity is constant to a very large distance beyond the location of the sun, and that has been extended by modern observations to a very great distance of almost 100 kiloparsec. And you see that the law of rotation of a galaxy is such that the orbital velocity is absolutely constant, and as you would expect it to decrease as 1 over square root of r beyond the extent of the galaxy. So either Newton's laws are wrong or something more basic is happening. So now let us look at rotation curves of external galaxies. Because you have powerful radio telescopes now, such as the GMRT near Pune, you can do this observation far more easily by pointing the telescope at an external galaxy, and because you have tremendous angular resolution, you can point it at various distances from the center of the galaxy and in a very routine manner plot the orbital speed as a function of distance from the center of the galaxy. Here are 4 galaxies up to 25 kiloparsec. You notice that in all of them, the circular velocity is dead constant. Now, we should have anticipated this. Let us revisit Oort's constant, A and B. That's the definition of Oort's constant. Now notice, I said that A minus B will give you the circular velocity of the solar neighborhood. We deduce from that it is 220 kilometers per second. But if we add A and B and not subtract A and B, then you find that because this is minus sign, the second term cancels out. So A plus B is simply d theta by dr. Okay? D theta by dr. I've used this identity over there. Now, let us take the modern values of A and B, 14.8 kilometers per second per kiloparsec, and B is minus 12.4, and you find that A plus B is very nearly 0. In other words, Oort's constant themselves are telling you that the angular velocity or the circular velocity is a constant as a function of the galactocentric radius in the solar neighborhood. Of course, now we have, using 21 centimeter radiation, seen this to be true over very large distances. So to summarize, suppose you are dealing with an external galaxy. This is the visible galaxy, which I have put over there. So you would expect that inside the galaxy, the circular velocity should increase, and it is increasing. But beyond the extent of the galaxy, you notice there is no luminous galaxy beyond this radius. You would expect it to decrease as 1 over square root of r. It is anything but decreasing. It is even increasing in some galaxies. In most galaxies, it is about dead flat. So what does this mean? Well, for various reasons, we can discount the possibility that Newton's laws or inverse square law of gravitation is wrong. Because if you abandon Newton's law, you run into serious problems at cosmological distances. So let us explore the other possibility. It implies, a flat rotation curve implies that there is a great deal of dark matter in the galaxy. Why do we conclude that? So let us look at that. We said if you're inside the galaxy, G mass interior, G m less than r, capital M, multiplied by small m by r squared is equal to the centrifugal force. Therefore, the circular velocity or the orbital velocity is square root of gm over r, where capital M is the mass interior to the radius r. Now, if the circular velocity is constant, if v is constant as a function of r, then it means that m of r in the numerator inside the square root sign must increase linearly with r. Therefore, the r and r cancel out and the orbital velocity will be a constant. In other words, the implication of a flat rotation curve is that the mass interior to radial distance r is proportional to r. Therefore, as you go to larger and larger and larger radius, the mass of the galaxy is increasing. But there is no mass that I see. The visible galaxy has ended. You say, well, look in ultraviolet, look in infrared. Sure, I'll look, but the visible galaxy has ended at some point. But a flat rotation curve extending to 20, 30, 40, 100 kiloparsec tells me that the mass of the galaxy is increasing proportional to the radial distance that I'm going out to. So what is this mysterious mass? This mysterious mass is given the name dark matter. So there is our galaxy. Beyond the galaxy, you would expect the rotation curve to drop as 1 over square root of r, according to Newton's laws or Kepler's laws. But it is constant, and that implies that the mass of the galaxy, regardless of the fact that you don't see anything luminous, going on increasing, which means that there is a huge halo of incredible mass, and observations tell us that the mass in this magenta halo of dark matter is 90% of the mass of the galaxy. And this is what we find in galaxy after galaxy after galaxy. So 90% of the matter in the galaxy is dark matter. What is this dark matter? Well, we know two things. It is non-luminous, that's why we call it dark. But we know that it exerts gravitational influence. Otherwise, the rotation curve will not be flat. So whatever this matter is, it behaves as far as gravity is concerned like electrons and protons and neutrons and pi mesons and so on, or in other words, baryonic matter, matter that we are familiar with, matter of which we and the planets and the stars are made of. We also know that whatever this dark matter may be made of, those particles interact extremely weakly with the matter that we are made of, that we are familiar with. Otherwise, we would have detected this matter a long time ago. Do we know of any such particle? A particle that interacts extremely weakly with matter? Yes, we know. It's the neutrino. It has a very small mass. You will say, no, neutrino has a zero mass. Neutrino does not have a zero mass. It has a small mass. We will discuss that in one of the later lectures. And it interacts extremely weakly with matter. In fact, it took about 25 years after the prediction of neutrino by Pauli in 1933 before the neutrino was detected in 1958 or thereabout. So could neutrinos be this dark matter particles? And the answer is no. For a while, cosmologists believed that dark matter particles could be like neutrinos. In other words, there could be particles that move very fast, almost with the speed of light. They were considered to be hot particles because they are moving with high velocities. Well, this idea that the dark matter in the universe consists of small mass particles which interact very weakly like neutrinos, but which move with the speed, essentially with the speed of light, had to be discarded. Because although the neutrinos have a small mass, they essentially travel at the speed of light. Therefore, it is very difficult to imagine neutrinos condensing to small lumps of the size of galaxies. Now, as long as you're dealing with objects like clusters of galaxies, which consists of thousands of galaxies, it is conceivable that you can imagine neutrinos condensing into a gigantic cloud, and the whole cluster of galaxies is embedded into this cloud. Unfortunately, astronomers have found that even in dwarf galaxies, let alone galaxies like ours or larger galaxies, even in dwarf galaxies, the rotation curve is flat. Therefore, even dwarf galaxies, which are very small in size compared to our galaxy, have dark matter halo. Therefore, whatever this dark matter particle is, it cannot be moving at the speed of light because it cannot condense into a very small size because of its very low mass and moving essentially at the speed of light. Therefore, dark matter cannot be hot particles, namely particles traveling at ultra high speed. Dark matter particles have to be cold, and they have to be very massive and yet interact very weakly with normal matter, with baryonic matter. Well, in the standard model of elementary particles, which unifies weak forces of radioactivity, electromagnetic forces, and strong nuclear force, there are no such particles which are massive and which interact incredibly weakly with matter like neutrinos. There just aren't. Therefore, if you were to look for an elementary particle with these properties, you must look beyond the standard model. Now, it turns out that for a variety of reasons, for the last 20 or 30 years, physicists have been trying hard to construct theories that transcend the standard model. Why they want to transcend the standard model, we shall not digress to discuss that. One class of such theories going well beyond the standard model is known as supersymmetric theories. What is supersymmetric about it? This is what it is. In such theories, such supersymmetric theories, for every particle that obeys Fermi-Dirac statistics, like the electron, proton, neutron, and so on, there is a partner particle, a supersymmetric partner particle that obeys Bose-Einstein statistics. And vice versa. Similarly, for every particle, like the pi meson, which obeys Bose-Einstein statistics, there is a partner, a supersymmetric partner particle that will obey Fermi-Dirac statistics. So that is the supersymmetry. It's the supersymmetry between the two statistics, namely the Fermi-Dirac statistics and the Bose-Einstein statistics. Now, let's not worry about what that has to do with the price of fish, as they say. The important thing is, in such supersymmetric theories, there exist weakly interacting massive particles. These are known as WIMPs, weakly interacting massive particles. Now, these theories may not be relevant for real world, but that's not the point. These theories that physicists are playing around with do admit the possibility of weakly interacting extremely massive particles. Particles are very much more massive than the neutron and proton. Now, many physicists believe that the pervading dark matter could be made up of these WIMPs. And these WIMPs were obviously created when the universe was very, very young, and the supersymmetric theories were the rule of the universe. Therefore, these WIMP particles are trapped in planets and stars and in intergalactic space and so on. But other physicists who are playing around with different kinds of theories believe no, the dark matter is made up of axions, different kind of particles that interact, which are massive but interact extremely weakly with matter like neutrinos. But then there are other physicists and astronomers who believe no, you don't need to discard the standard model of elementary particles, that this dark matter could consist of a very large number of tiny black holes. They call them machos. So the galactic halo is full of these black holes, which we haven't yet detected. Well, we don't know what is true. The important thing to appreciate is that there are several major experiments costing billions of dollars, very large experiments, to directly detect these weakly interacting massive particles. Now you may say, it's going to be very difficult because they interact very, very weakly. Yes, that's true, but after all, the neutrino was detected. What you need if something interacts very weakly with the detector is a very large detector in a place where there is very little background noise. So they build these experiments inside tunnels, inside the Alps mountains, or deep under the sea, or deep under the ice in Antarctic, and so on. These experiments have been going on for the 10 or 15 years, and the idea is that sooner or later we will detect these relic particles that were created in the very early universe. So far, the experiments have not yielded any results which are statistically significant. But that doesn't mean they will not do so in the future. After all, it took a very long time, 25 years, to detect the neutrino. Now, if you wish to know more about these experiments, they are beautiful, fascinating experiments. The principle is extremely simple. An axion or a WIMP collides with the nucleus, and the nucleus recoils, and then it emits some radiation, and you detect this radiation. Or you detect the heating of the body because this nucleus that has been kicked gives its kinetic energy and heats up the material. So these are the kind of principles. But these are incredibly difficult experiments requiring tremendous signal-to-noise ratio before you can detect them. So if you want to know more about it, I suggest you go to the ASI website that is given in the poster, and there Dr. Sushant Konar will give you some references to these experimental setup. So that is the summary of how we deduce the law of rotation of our galaxy and what it has led us to, namely that 90% of the mass of the universe is in the form of dark matter whose nature is totally mysterious. And in the next lecture, we shall discuss the spiral structure of galaxies, why these spiral structures arise and why they are stable. Thank you very much.